No. No, it's not working. Okay. Good day, everyone. So here you see our group. We were 11 people on a boat, plus the wonderful crew of this Ulla Riedman. And this boat allows us to do the logistics, to go there and stay there for 2 weeks and do sampling and at the same time do geophysics. And that was our base station. And also we use the boat a lot to navigate. We were very happy with the weather, by the way, and very happy with our team, because it's a kind of very narrow environment and you stay very close to each other and you have to be nice to each other. And luckily everyone was nice, and therefore we collected data. And also thanks to organizer, to Kim. The project, so why I went there, so how we organized it. So we just split it, so with the own contributions, and then we had many different projects. You will hear about this. And people are interested in different stuff, in fluid chemistry, in the magnetic properties, in the petrology, volcanology. And we just came up together and try to do common things, but at the same time something different to fulfill the goals of our project. My project I'm working on, it's called Dipole, and Yanagi Falaida, he's used to be a leader of this until recently. So now he handed over to Carmen Gaina. She's online. But the project is about Svalbard passive margin and the Gakkel Ridge. So, and in this project, related to that, we collected 2 types of data. One type of data is seismic data. This is a refraction profile with OBSs, which we acquired under the ice. And 2 multi-channel profiles, which has been done in 2022. So both the seismic lines. And this area is an area of MT survey, which is links with the development of the passive margin, because it's like a volcanoes which directly can be observed on land, yeah, and it can be linked to the opening of this margin and extension. So what about the magmatic history here? So this margin, despite it's called magma poor, it's still quite magmatic, and the magmatism happened at different times. And the first, it started with the opening of the Arctic Ocean. When there was no Arctic Ocean, the Arctic Ocean started formation about 130, 125 million years ago. And at that time, there was intrusive volcanism, and the Svalbard field is filled by giant dikes, which are radiating from this large igneous province somewhere up north. What's happened afterwards? So afterwards, there was not too much was happening within this area. At least there was no observed rocks, neither sedimentary nor volcanic, because it was uplifted and then it was staying until about 53, 56 million years, when this basin started formation. And this basin is called Nansen Basin or Eurasia Basin. approximately soon after it started forming here, so a few millions after, probably, there was a volcanism on this area, which is called Yermak Plateau. This is extended continental crust, reworked with the volcanics. And this considered to be a part of the passive margin which was extended. When and whether it's a one episodes or a long history, we don't know. There's no much data. But we know that the youngest sampled volcanic mount in this small basin between this volcanic plateau, partly continental, and Svalbard, has an age of 13 million years. And this is quite close to the Miocene lavas on Svalbard, and also it's very close to the first magnetic anomaly, which is Cephalospreading magnetic anomaly, which is passes through. Yeah. So, but we would say, so the story should end on this, right? So, okay, so you formed the ocean and you should be happy, no volcanism. But no. So, about 1 million years ago, or even younger, I don't know. So there was started like the area started to be volcanic again. Yeah. So and we see at least three volcanic centers: Sverefjell, Haldanpiggen, Sigurdsfjell. So and all of those are quaternary, and those lavas are filled with olivine rocks, with mantle rocks, like I don't know. It's probably all, less basalt than olivine, right? Yeah. Or it looks like, because it's green. Yeah. So and this and here I'm talking about what we were doing with MT and how we image this particular strange enigmatic volcanic system. But we also have a poster, and the poster will be up there when we can learn more about development of this margin as a whole. And the poster would gonna be in afternoon. Let me put up, I'm a geophysicist, I like those maps, which gives a kind of a regional representation of what's going on right now. Yeah. So what's happening? Here is a distribution of seismicity, and follows the plate boundary generally. So on Svalbard, and this area is also seismically active, which is unusual. In the largest earthquakes happened in Norway on Svalbard, and with magnitude 6.8. So, and this is also quite can be attributed to various processes, starting from the glacial to tectonics. But since there's only a few stations, we don't know the actual distribution of the earthquakes on Svalbard. Maybe it's extending over there. There's a gap. There's no stations there, so we don't know. The only reason why we have earthquakes there, because there was a temporary array installed in 90s. So otherwise we wouldn't know that there is a seismic activity in this area. But what is color? The color is dynamic topography, which is calculated from the residual gravity anomaly. So this area standing high right now and uplifting very fast. So we don't know why also. And here on this map, it's a compilation of the viscous relaxation time. So if we map the beaches and we collect shells, and then we can actually date the terraces. And from this data, we can calculate how fast the land was uplifted after the glaciers melted. Yeah, and in this area, it happened very fast. So basically, within 1,000 of years, all the beaches were up. Yeah, after the glaciers melted. Yeah, here it's about 4 times slower. So we see generally, if we compile all this data, so we will see the trend that here the area was uplifted very fast and here so very slow. So why? This rate is related to the properties of the mantle. So if mantle has a very small viscosity, so then it's all this perturbation relaxes very fast. Yeah, and if the viscosity is very large, so it's more slow process. Yeah, so therefore we see that there is a trend. So and actually the minima of this in the area exactly where we have those volcanoes. Yes. Uplift rate present day. So actually there is a trend similar way, and it's I don't remember, was it 1 centimeter even, right? So yeah, yeah, yeah.
But it's very quite low laterally.
But it's present day. It has been shown for Greenland and for Antarctica that uplift rates are higher present day in the areas of the weak mantle or some temperature anomalies. So why is that? There are different hypotheses, and one of the hypotheses that present day ice melting due to the climate change uh, somehow controls this. That you remove that ice is removed so fast. Somehow it can be linked to the properties of the mantle. I don't know whether it's true or not. We should ask Sergey, maybe later on in the.
This picture is nothing, not much to do with the recent. This data is based on last
Yes.
5,000 years, and if he says that the relaxation was within 1,000 years, then the left north the corner is actually already.
Yeah. So
it's kind of independent interpretation. What is rates are now, and what is this picture about?
So we can discuss it in the break, right? So and it's an interesting. And this comparison. So you see that's another correlation that if you take the average seismic velocities within the lithosphere S-wave tomography model, that it's also pretty nice correlation with relaxation times. Okay, so this is motivation. Why we went there and deployed 12 stations. The original plan was to make it like a long period stations deployed for 3D, deployed for the 2 weeks. But in reality, we had to go for broadband and deploy for 1 day. 2 stations at the same time, and these are squares here, and we deployed on the beaches which are accessible by the boats, and some around Sverifjell, this volcano, and this is a big fault, and this is a sedimentary basin. So mainly we were sampling sedimentary basin. Why? Because it's accessible. So we have those like a fence, sedimentary, and the flat spots. So the difference of geophysical party because it's a beach party, and the geologists, they go up. Yeah, so they always like were very jealous when I was sitting with my equipment, so they had to go with the backpacks up. Yeah, and I'm sitting relaxing on the beach. Yes, and this is how the beaches look like. So we installed some close to this troll Sheldon, some around Sverifjell, and this Sidefjell formation. It's on top of the Devonian strata. And how they came through the conduits, and one of the conduits is observed, this enormous finger, and yeah, crazy. So this is how the general beach party installation look like. So we have what is magnetotelluric? So we basically have magnetometers, horizontal components of these tubes, and it's not just like it's actually plastic tubes which you can buy in a shop, but inside it's a coil, and it's an induction magnetometer. So there are variations in geomagnetic field in the ionosphere due to the variations in the sun, and these variations which induce also the secondary field within the conductive earth is recorded with two stations. Yeah. With two magnetometers. And we also have a pair of electrodes, which is difficult to see where they are here in the stones, but we have cables extended to like a 50 meters long. So, and what we measure the electrical field, the voltage between those two electrodes. And so we can relate the relationship between the magnetic and electrical component horizontal to the conductivity within the Earth. So, and this is how the time series look like. So basically the quality is shown that we have some correlation between the horizontal X electrical component and Y magnetic component. So we see that there is some noise, but there is a quite good correlation between them, and the same for the other two components. How we do this? So we basically measure this, we measure this. So the goal is to estimate this complex thing, which is called impedance tensor. And this impedance tensor is a complex tensor. So what we do, and this is relation and also in the frequency domain. So those things are like Fourier transforms. So, and what we do, we actually analyze all the time series within we chop it into the small pieces, and then we do like a statistical analysis, regression to find those coefficients, the transfer functions. So the more data we have, the more robust estimates. So for this, we also do the what is called remote reference processing. So we have two stations measured at the same time, and so we can, and then the noise would cancel out if it's not correlated. So we just multiply it here to estimate those, and then we can cancel unwanted signal, unwanted noise, due to various reasons. So then also we can use the magnetic observatories on the on Svalbard and include into this robust processing method, which is designed by the person I borrowed the instrument. Maxim Smirnov is working on Lule Technical University, and I borrowed instrument from him and a lot of guidance he provided in this work. So this is the observed and modeled transfer functions. So what is called, and here they're displayed in terms of the apparent resistivity. And apparent resistivity, it would be the resistivity of the Earth if it was 1D Earth. Yeah. So we see some are very resistive, 100 ohm meter, and some are more conductive areas. And in the black, the dots with these arrow bars, it's observed component. In this case, it's YX. And the red one is the result of the modeling. So we try to fit, we design a model in 3D and invert this data in iterative fashion, yeah, to fit the and defined electrical resistivity. And this is the model. So preliminary model, the data still needs to be processed with the additional remote reference. But what we got so far, it's a signal of up to about 12 kilometers, which images the upper crust. Yeah, and here the slices from the very shallow 750 meters towards the 11 kilometers. And what we see, we have those conductive anomalies. They're normally quite better imaged by the MT method. And those conductive anomalies, they're sitting within the generally correlates to the basin, to this Devonian basin. And there's some more resistive areas which are supposedly close to Halvdan-Pigen and close to Sverefjell. Those resistive areas must be correlated with the volcanic region. And if we compare the geological rough cross-section, so we see here the area is a resistive area of the basement, Proterozoic basement rocks, and intrusions. Maybe this blob, very resistive, may correspond to the Sverefjell itself. And we have a conductive zone below this basin. And then in this area, so whether we pick up the basement or it can be also related to the intrusions in the sedimentary cover. The resolution, we are losing resolution in this area. So to conclude, so it's the first 3D survey, semi-regional, or the first ever 3D survey MT on Svalbard, which is accompanied by sampling. And this was the data of good quality acquired, and the preliminary model shows the architecture of the Devonian basin interaction with the mice.